All right, so just a brief comment about the idea of giant red supergiants. We heard earlier about this. The point is being that the scale height, this, what would you call it? The energy factor, the ratio of the energy to the thermal energy, the escape energy to the thermal energy, I think is what you call the DOE or HEP, sorry. Anyway, that gets lower and lower for giant stars. So that means it's getting closer and closer to having internal energy enough to kick things away. And you see these giant convection cells that are formed relatively deep, where the sound speed's higher. And then they basically, in the talk by Selma, talked about this and how you could have. My idea is that this is just the way that the material finally spills over, but it's because the star has become a giant that it's doable. All right, so then that's kind of a little bit analogous to this iron bump that Norbert talked about. So I got involved with this through Yorick and Butch Greifner and analyzed this, what happens when you get this iron bump. And then what happens is if you want to stay above at the Eddington, that you have to go over this hump. Okay, and so you're going over the hump, you lower the density stratification. And I came up with this simple idea about how you could estimate the inflation factor. Basically comes down to plotting the density, inverse of the density, against radiation pressure, which is just temperature. And what is the width of this curve? And you don't see it there, but there's a kind of shaded triangle. And you know how to integrate a triangle. It's a trapezoidal rule. It's half the area times the height. Anyway, the point is that you can just work out how much inflation occurs. You come up with this relatively simple formula for the inflation factor. And it turns out to be, this formula. And you can see if W gets close to 1, then you're screwed. There's no static photosphere, right? All right, so what does that mean? Well, it means that you can maybe have a flow induced by the iron bump. Who's been working on, anybody here had that idea? Okay, so obviously John's group is doing awesome work on this. I mean, really impressive work. And Luca, for example, has these beautiful models where he tries to go with the iron bump and you start a flow, you start an outflow. W is basically the ratio of the flow energy to the gravitational binding energy. You get a little bit going, but it's not nearly close to the escape. This is going to be the units of the escape energy. And you get it up and it basically falls back down. It's a failed wind. We talked about yesterday what we should call this. Well, I think it's basically a failed wind. It's not convection. It's no more convection than if I throw a pencil up in the air and it comes back down. You overcome gravity here, but that's not enough to make it escape, right? So that's what the iron bump is doing. And the point is because the iron bump is not gas pressure, it's radiation pressure, the effective sound speed, the pressure over the density can be very, very large compared to what it is for gas. Anyway, that means you can get very high speeds. And so here's the kind of thing that Luca finds for Wolf-Rayet stars. You start off the iron bump, you kind of get going and you stagnate, but then line driving takes over because the opacity at the iron bump is computed with the Rosslyn mean, which is the inverse harmonic mean. But it's made of a bunch of iron lines. And as soon as you start having a large velocity gradient, those lines deshadow and they become CAK-like. And so once you can do that, then you can kick on the CAK solution and you have this kind of two-stage evolution of the wind. As I said, that's like the water bubbler, right? It's like the water bubbler getting the water off the fountain and then something else sucks it away, line driving. Okay, where are we now? And then here's these beautiful models that Nico's done of this whole process. And lots more to do in this. All right, so as John mentioned, I gave this talk on Thursday last week at the XUU meeting. And I was supposed to review, Yorick asked me to review iron bump stuff, convection, turbulence, and line driving. And me, I always have to figure out a simple way to understand, get estimates, scaling laws. That's what I cut my teeth on, right? And so I went through this analysis, which basically said, the speed, the kinetic energy that you get is just the work that you do. And then you put this in, you change the rate of acceleration with this radiation pressure term. But, you know, this is the nice thing about being a physicist is that you can use the Leibniz notation to cancel stuff, you know, and you end up getting this, it ends up being just a jump over radiation pressure with density in there. And you're coming an estimate for how much the velocity is, and it turns out to be the ratio of the radiation pressure to gas pressure times the gas sound speed. And then that's just the plasma, what's called often the radiated beta, the ratio of gas pressure to radiation pressure. And you can estimate what it should. It's on the order of 70 kilometers a second for a beta of 2, say. Beta of a half, I'm sorry. And it gets even higher if you go higher. And that's what you see. You see turbulence that's 100 kilometers a second. Now, wait a second. What's the sound speed? Sound speed is 20 kilometers a second. Can you have turbulence that's supersonic? What do you think? Well, you can if it's not running into itself. If it's a sound wave, it's a P mode in the language of the pulsation people, it just steepens into a shock and it dissipates, becomes heat. But if it's a circulation, it's throwing a ball up here and coming down there, there's no reason you can't make that go fast. You know, if you didn't have air resistance to worry about, you could throw a ball up in the air and it could go a substantial height and fall back down somewhere else. And until it hits the ground, it's not going to make any shock or anything. So the point is this, you can have very highly supersonic turbulence. And the net result is you can characterize this as a change in this parameter, this energy parameter. It's normally very tiny, the ratio of the sound speed to the escape speed. The scale height of a star is very, very small compared to the radius, just like it is for the Earth. Why is it that you can go with this line at 100 kilometers up in the air and we say we're in space? Because the atmosphere is confined to that small scale. You go into orbit at 200 kilometers, you can just stay there for a long time without much atmosphere dragging on you. Well, the same thing is true for most main sequence stars. It's only the giant stars that the scale height to the radius becomes comparable, or an order, maybe a tenth or something. But most stars, it's 1/1000. But now, if you have this this turbulence, the scale height is now, 26 times bigger because it's Mach 5, and that makes the atmosphere much more bloated. And now your problem with getting through the sonic point might be a lot easier, right? And I think it's a little bit related to you using very high sound speeds in your calculation. Anyway, so this might have ramifications. John's already started thinking about this, I know, of getting past this problem with getting past this throat problem of when you put in the full non-Sobolev forces. But it only works for supergiants, for stars that are close enough to the influence to have lots of turbulence. What happens when you go to the low luminosity stars? You don't have the iron pumping, very important. You don't have as much, observationally, you also don't have as much turbulence. And now you have to really work to make this wind work. And you choke it, you make the mass loss lower, and that becomes what we call the weak wind problem. John, I think, can talk about that a lot more than I can. All right, now comes one of my, this is where your eyes start to glaze over it. I know Susie has already glazed over a long time ago, but this is where everybody says, what the hell is he talking about? Because I myself didn't learn about this until I was at KITP talking to Philip and other people. Elliot Catart and I got into a big debate about how radiation driving works. And to a person who works in the interior, it's a gradient of a radiation pressure. I always said pressure-driven winds was not a very good name because it's not the pressure, it's the flux. Deep inside, the pressure is related to the flux by the difference in pressure. But the surface, it's free streaming, it's not a difference in pressure, it's not very well described that way. But it turns out when you go deep inside a star, the radiation transport by diffusion gets harder and harder because the optical depths are harder and harder. And if you just have a little bit of flow, you can advect the enthalpy. And this becomes a way to have an enthalpy advection. And so this is really quite important because what ends up happening is we already talked a little bit about this in whose talk was that? Peter's talk. There you go. He's right in front of me. And this is what happens when you get old. You forget people's names. Sorry about that. But anyway, the point is that this is exactly the term that he was talking about in his LBV simulations. And at some point, the advection of energy beats out the flux transport, and that completely changes the nature of the wind solution. And there's these nice graphs that Rich made. Rich was instrumental in me doing this work because he mastered at solving the equation that we had to solve, 2-point boundary condition. Anyway, you got all kinds of really interesting results in this paper. It's pretty technical, but John's group is up to it. They can get this. And I want next week to push this paper. All right, here we are. Joe, sorry, we're back to Eta Carinae. Because as I said yesterday, when you've been given a gift like this, a star, 2.5 kiloparsecs away, we have historical records of its explosion or its eruption. You have beautiful multidimensional spectra, and this is your Rosetta Stone. What the hell's going on here? Well, first of all, it's a binary today, as we were talking about. And the binary is a highly eccentric. And every 5.5 years, it makes all these X-rays. And Atsuo came to visit for his sabbatical in 2012 or something like that, was it, Atsuo? I think so, around that time. And he did these beautiful 3D SPH simulations. Now, if you talk to people in the hydro community, SPH, oh yeah. Well, you try doing a 3-dimensional model of a colliding wind over the huge dynamical range with a grid-based code, and and it turns out you get a lot of the physics with SPH. There's this purity test in hydro. Some people are, oh, you can't do SPH because it's diffusive and all this stuff. Well, yeah, but it can still teach you a lot. And it's better than just imagining in your brain what's going on. So anyway, this is the calculations, and there's a nice movie. And of course, Chris Russell did this for his thesis. Anyway, he basically calculated light curves from this model and basically showed that you could explain this X-ray light curve with basic hydrodynamic modeling. He also has these beautiful movies of the X-rays, but I think I actually still have it, but I'm onto it. All right, so now that leads to the stuff that Nathan's gone now, but back to the wind compressed disks being inhibited by this oblateness and gravity darkening. And what happened was, I was at the AAS after I had proven that you couldn't use the wind compressed disk because all these effects of oblateness would kill it. I went to the AAS meeting and Nathan was there. And we sat down at a place where a bunch of stellar people were sitting. And right there is Neil deGrasse Tyson. So I had a chance to meet Neil deGrasse Tyson, Now I can tell you a little bit about my Buzz Aldrin story if we had time, but maybe you can ask me about that later, because I also had a chance to meet Buzz Aldrin once. So Neil deGrasse Tyson, Buzz Aldrin, it's pretty good. Never met Mel Gibson, but anyway, the point is that the more rapid rotator, you get more mass loss over the poles and higher speed. And Nathan has these split factories he talked about already. He saw evidence in the H alpha, the Piscini trough, that this is exactly what's going on. Now there's some debate. Jose Gros argued that you get this from just the binary and stuff, but Nathan, they had kind of we had a debate at Delaware. I invited Jose to come and Nathan, and we kind of had a square off, and debate is not bad. We got to debate if we're going to learn stuff. Okay. Anyway, this is suggested to me that, yeah, maybe my models actually can explain the reality. That's pretty amazing. All right. So here's this man, Arthur Eddington, right? And, did amazing things, including the Eddington limit. There is super Eddington, right? And so we want to know what happens if a star somehow gets above the Eddington limit. There's me giving a lecture at Cambridge. When I was visiting Philip in Oxford, he arranged to have me invited to go give a lecture at Cambridge. Unfortunately, it was really hot that day, and I'm sweating like a pig, as you can see. But I'm giving a lecture on the Eddington limit in Eddington's library. It doesn't get any better than that. Okay, so there is the idea that goes back to Nir Shaviv. Nir, as he told you yesterday, had this idea about porosity. The problem with the Eddington limit is that once you go above the Eddington limit, the whole star goes above the Eddington limit. So how do you regulate? Well, the answer is deep inside the star, it becomes convective, but there's also, as it becomes structured, then photons go around the structures and you get a critical point due to the porosity. So Ken and I and Nir came up with this model for how to moderate the radiative driving above the Eddington limit with porosity. And it's basically completely analogous to the CAK theory, except for the power laws and the porosity. And then there's Alidjan, who was working with me. And we did this beautiful, he did this beautiful simulation, very similar to the stuff that I think you showed, Peter, or other people, Nico. Yeah, I think it was you, Peter, that showed flat, very similar to this, but this is a one-dimensional model with, and now there's a question of whether you can drive a flow with just the internal energy of the gas. The answer is if it's radiation, you can. It's gamma equal to 4/3, but not with its 5/3. And so then there was this beautiful work beautiful set of simulations that Rio did, which then allowed me to find out when you added the energy to an envelope, 1D, just from like say a fake merger, then what happens, you induce shock and then you make the material near the surface become unbound. It's Bernoulli constant is positive. And the net result is that a lot of material gets kicked up and escapes, but some material falls back down. And the net result, and this is, I still think this is like one of the coolest things I ever, I mean, I guess other people have found hints of it, but I don't understand why everybody thinks this is really cool. That the density of the different digital fluid parcels follows, you might expect if it's expansion, it's following a similarity solution, that it should fall off like 1/time cube, just like the universe gets less dense over time. But there's a connection between the radius and velocity and this parameter, V naught. V naught is a characteristic parameter. It's related to the escape energy of the star. Rio and I don't agree about that, but that's okay. And there we are in Oxford. And I learned a lot. I learned a lot from Philip and Rio, and Fabian was in this picture as well. It was one of the most pleasurable combinations of pleasurable, beautiful place to visit and having great science. And then Rio's already shown you this picture of the idea that this led to. Nathan also had very similar ideas. Nathan's also on this paper. And I believe it's not, maybe not 100%, everything's, all the I's across, all the I's are dotted and the T's are crossed, but I think it's basically a merger. And I think Eta Carinae was a merger. I think the evidence for that is pretty overwhelming. And why is it so interesting? Because we now know with time domain astronomy, we're going to discover gobs